In the next part of today's lecture, we're going to cover a little bit of imitation learning theory building off of this notion of cost functions and reward functions. So we'll ask this question: what is a good cost function or reward function for imitation learning? So this is the sketch of imitation learning from before. We're going to be mapping observations to actions. And we could hypothesize that maybe a reasonable reward function might be the log probability that we assign to the expert's action. So the log probability of the action that we take is equal to pi star of s, where pi star is the unknown policy of the expert. We could also use something called a 0-1 loss. So we might say we get a loss of 0 if we perfectly match the expert and a 1 if we didn't. The 0-1 loss is a bit more convenient for theoretical analysis, and it directly counts the number of mistakes that you make, whereas the log likelihood is a bit more of a practical choice. But remember that in reinforcement learning, the reward or loss must be evaluated in expectation under the learned policy, not under the policy of the expert. So we want to match the expert's actions in the states that we actually visit, not necessarily just in the states that the expert visited. And this is why behavior cloning is not actually optimizing quite the right objective. Behavior cloning would typically maximize the log likelihood in expectation under the state or observation distribution of the expert, whereas we want to maximize it in expectation under the state or observation distribution of our policy. This is another way of saying that we have a distributional mismatch problem, and this is exactly the problem that Dagger tries to correct. So what I'm going to do next is I'm going to theoretically analyze some bounds on the expected cost for naive behavior cloning and discuss how we can formalize this distributional shift problem. So in this analysis, I'm going to use capital T to denote the length of the trajectory. So if we see me use capital T, that just means there are capital T steps in our trajectory. And we're going to be concerned with this 0-1 loss. And the quantity that we want to analyze is the expected total value of the 0-1 loss, which is also the expected number of mistakes we would make along one trajectory. So in order to do any kind of analysis like this, we have to first make some assumptions. And the assumption that I'm going to make is that supervised learning works. What that means is, initially, I'll make a fairly naive assumption, which is that for all of the states in the training set, the probability of making a mistake at those states is less than or equal to epsilon. This is a reasonable assumption because it says for the state and action tuples that you saw, you learned them effectively, meaning that if someone told you in state S take action A, you're going to assign a probability less than or equal to epsilon to every other action, where epsilon is some small number. And now, in order to think about bounding the total number of mistakes, we're going to consider the most pessimistic scenario possible. When we construct theoretical bounds, we want to be pessimistic. We want to write down some inequality that holds in the worst possible case. And the most pessimistic scenario for these 0-1 losses is what I'm going to call a tightrope walker scenario. So for a tightrope walker, the tightrope walker needs to take exactly the right action at every single point in time. And if they make even a single mistake, they fall off the tightrope, and then they don't know what to do. So we can illustrate the tightrope walker schematically as this grid world, where they have to stay on the gray squares and keep going to the right. And if they deviate even once, they fall off, they go into the red region, where there is no demonstration data because the expert never fell off, and therefore they have no way of knowing what to do. Now, this tightrope walker, just to be clear, is not concerned with falling off because they'll get hurt. They're concerned about falling off because they will incur 0-1 loss. When they fall off, they'll be in a state where they have no data, which means that they have no way of knowing what to do in that state. So it's a kind of a funny tightrope walker. Their concern is not about hurting themselves. Their concern is about not knowing what to do. Okay, so let's analyze this tightrope walker. So the quantity that we want to bound is the sum over time of the 0-1 loss, which is the expected number of mistakes. Let's think about the first time step. At the very first time step, the tightrope walker starts in a state that was in the training set, which means that with probability greater than epsilon, they will take the correct action. With probability less than or equal to epsilon, they'll take the wrong action. If they take the wrong action, they will fall off, but they still have capital T time steps left. And once they fall off, they have no way of knowing what to do. So if they fall off, they will make an additional capital T mistakes. So we can say that for that first time step, there's an epsilon term which represents the probability of falling off. And if they fall off, they will get capital T additional mistakes. So there's an epsilon times capital T term, and then there's a 1 minus epsilon times everything else. So epsilon times capital T plus 1 minus epsilon times the number of mistakes that they will make at the next time step until the end. And what happens at the next time step? Well, the same exact thing. At the next time step, if they did the right thing on the first time step, they again have an epsilon probability of falling off. Now there's only t minus 1 steps left, so if they fall off on the second step, they will get epsilon times t minus 1 plus 1 minus epsilon times whatever's left over. So you get this series of terms, epsilon t plus 1 minus epsilon times epsilon t minus 1 plus 1 minus epsilon times 1 minus epsilon times epsilon t minus 2, etc., etc., etc. So you basically get capital T terms, and each one of them is on the order of epsilon t. Right? When we're concerned with big O, we can get rid of constants in front. And since 1 minus epsilon is usually a pretty large number, all we're really getting is a bunch of these epsilon t terms. So that means that the total bound is capital T times epsilon t. So the error is on the order of epsilon t squared. Right? Technically, it's going to be like epsilon times t squared over 2 or something like that, but if we're just concerned with big O, then we don't care about those constants, and we get epsilon t squared. Now, this is a pretty bad bound, because it means that as the length of our trajectory increases, our error increases quadratically. And that's why naive behavioral cloning can be a bad idea, theoretically. Now, that analysis was a little bit naive, because we didn't assume anything about generalization. We just said that for all states in the training set, our error is bounded by epsilon. A more general analysis would account for generalization, would account for the fact that your policy does well not just on the training points, but on other points from the same distribution. So one way that we could say this is we could say our error is bounded by epsilon for any state sampled from ptrain. In fact, it's actually enough just to say that our error is bounded by epsilon in expectation for ptrain. And that's much more realistic because that's our actual training objective. For the analysis I'm going to present, I'll go with the S sampled from ptrain definition, but this is actually fairly easy to extend to the setting where your expected error is bounded by epsilon, and that's what's actually done in the Stefan Ross Dagger paper. So here's how we can go about this more sophisticated analysis. So first, just to get this out of the way, with Dagger, ptrain approaches p theta, right? That's the whole point of Dagger. So if ptrain approaches p theta, then all points will be in distribution, which means that S is always sampled from ptrain, which means that error is always bounded by epsilon, which means that no matter what you do, the bound on the expected cost will be epsilon times t. It'll be linear in t. That's in some ways not actually all that interesting of a result because we're removing all distributional shift. What's more interesting is how we can show that the bound is still quadratic if we don't do Dagger, if we don't have ptrain going to p theta. And that's what we're going to do next on this slide. So if ptrain is not equal to p theta, then what we can do, and this analysis is basically directly based on Stefan Ross's paper, A Reduction of Imitational Learning and Structured Prediction to No Regret Online Learning, which is the Dagger paper. What we can do is we can write the distribution over states at some time step t as the sum of two terms. And these two terms are kind of analogous to the tightrope walker scenario. The first term represents what happened if we haven't made a mistake at any previous time step, and the second term represents what happens if we did. So for the first term, what's the probability that we haven't made a mistake so far? Well, our probability of doing the right thing if we're in distribution is 1 minus epsilon. And if we do the right thing, then we remain in distribution, which means that by time step little t, we have a probability of 1 minus epsilon to the power t that we've done the right stuff up until now. And if we've done the right stuff up until now, then our state distribution is simply p train, because we've matched the expert every single step up until now. So the first term is 1 minus epsilon to the power t times p train. The second term is everything else, 1 minus epsilon to the t. So this basically accounts for all the other probability mass. And if we have made a mistake in the past, in general, we can't really say anything about where we're at. So we might have fallen off the tightrope, we might be in some crazy place, so we're going to call that p mistake. So what this is saying is that at any time step, we can write the distribution over states as the sum of two terms, the first one for not having made any mistakes, and the second one for having made at least one mistake. Now in general, we can't say anything about p mistake. So for p mistake, we might have arbitrarily large probability of additional error. So what we can do is we can bound the total variation divergence between p theta st and p train st. Total variation divergence is just the sum of the absolute values of the differences between the probabilities over all the states. So if we take the left-hand side of this equation and substitute in the above equation for p theta, basically substitute in 1 minus epsilon to the t times p train plus 1 minus epsilon to the t times p mistake, the first p train term cancels with the minus sign, and we just end up with 1 minus epsilon to the t of the absolute value of p mistake minus p train. Now remember that we can't say anything about p mistake, so the only bound that we can put on the total variation divergence between p mistake and p train is the maximum error between two distributions, which is 2, right? Because the distribution is summed to 1. In the worst case, one of them will be 1 in one place and the other will be 0. The other one will be 1 in another place where the other one is 0. So the only bound that we can put on this is, if we don't know anything about p mistake, is 2 times 1 minus epsilon to the t. A useful identity that we can use to simplify this is that 1 minus epsilon to the t is greater than or equal to 1 minus epsilon times t if epsilon is between 0 and 1. And we know that epsilon is between 0 and 1 because epsilon is a bound on a probability, and probabilities are always less than 1 and always positive. So we can write a simpler bound for this by turning this into 2 times epsilon t. We don't have to do this. This is a looser bound, but it's just convenient to remove the exponential and to give us kind of an understanding of the big O magnitude of this. Okay, so now let's go to the quantity that we really want. What we care about is the expected value of the cost over all time. So we can write the expected value of the cost as a sum over time of a sum over states of the probability of that state times the cost. That's just from the definition of expected value. And we can express this. We can express a bound on this cost in terms of two terms: p train times the cost plus the difference between p theta and p train. The way that you get this inequality is just by writing p theta is equal to p theta plus p train minus p train. Right? If you add and subtract something, that's all good. Then we group the terms and we put absolute value around p theta minus p train, because the absolute value of a number is always greater than or equal to that number itself. So that's how we can get this bound. Now, the first part, p train times c, we know what that is because the expected value under p train of the cost is bounded by epsilon. That's our assumption. The second term, well, the bound that we have above on the absolute value of p theta minus p train is 2 times epsilon t, and c max, the worst case cost, is 1. So then the bound that we can write out for this is epsilon, that comes from the expected value of the cost under p train, plus 2 times epsilon t, which comes from the total variation divergence or absolute value between p theta and p train. So we have one term that's linear in capital T and one term that's quadratic, because the sum over t of 2 epsilon t is on the order of capital T squared. So we've derived an O of epsilon t squared bound with this kind of more general assumption. And notice here that the only assumption on the policy that we needed is that the expected value of the cost under p train is epsilon. So this is kind of the more general assumption that I stated before. All right, so this derivation maybe went by a little fast, so if you have any questions about this, do feel free to ask a comment on YouTube. We can discuss this in class, and also consider checking out the paper cited below by Stefan Ross that describes the full proof in detail.